Hi, everyone, and welcome. Thanks for joining the third episode of our Journey of a Packet webinar series. Today's episode is Packets Don't Lie. I'm Stacey Jambura, the event marketing coordinator here at LiveAction and your moderator for today. Today, I'm joined by Jay Botello and Chris Bloom, and they're going to be running through a discussion and demonstration regarding the importance of packet data when trying to analyze and troubleshoot your network. During our presentation today, if you do have questions, please make sure to enter those into the chat box, and we're going to address those at the end of the talk today with a little Q&A session. So with that, I'm going to hand you all over to Jay and Chris.
Thank you, Stacy, and welcome everybody to another episode of Packets Don't Lie. Today, I am here with Jay Botello, Senior Director of Product Marketing, and my name is Chris Bloom. How are things going, Jay?
Hey, Chris, doing well. Looking forward to doing this with you. It's going to be a great topic, right? Especially for people that don't do a lot of packet analysis and really want to know what is really in those packets and what am I looking at when I look at a packet. So it's going to be a great topic.
Absolutely. And we're going to run through many examples today. Well, not too many, but we've got a good collection of examples of, how packets can be used to verify the network, to troubleshoot the network, along the theme of packets don't lie.
Right, Chris. Right. We're capturing the packets. That's ones and zeros, the most basic rate. The way you can capture that data, and it's always there. Any analysis we do is built on top of those packets. You can always get back down to the packet, and through the rest of this, we'll show you why sometimes it's important to get right back down to the packet itself.
And on the point of capturing the packets, just real quick slide here. These are some of the products, our hardware products at LiveAction that you can use to capture the packets. We have hardware appliances from our small edge to our large power core that you can see can capture up to 40 gigabits per second. We also have a virtual version of that. So first of all, it's not easy to make sense of all the binary, the hex, or the ASCII. So we analyze the packets and we provide high-level views, different ways of looking at the packets to allow you to correlate this different information. But it's all coming from the packet. Whether it's the nodes or it's the protocols or even the decodes, when you're working with a protocol analyzer, in this case, OmniPeak, you really are working directly with the packets. And, Jay, we've got a couple of screenshots here of views I think give pretty good examples of how we can go from the low level decode, which is actually still pretty high level. We'll talk about that, up to higher levels of analysis.
Yeah, I think you're right, Chris. That view that's on the left, that textual view, that's the packet view. We're going to dig more into that here just in a second, right? But we have other, unique views over way on the right. It's nodes and protocols. Pretty straightforward. It's a list view. The view in the middle, that peer map, or what we call our peer map, so it shows all the different connections. It's a very unique view for OmniPeak. You don't get that in other products, and though this is just a screenshot, there's a tremendous amount of information in there when you're live with that data. Each of those lines, the thickness of the dots, you hover over any of that and it gives you a whole range of very useful information about the connection between those two IP addresses.
So, Jay, I think we should start with packet decodes, because that's really at the heart of any protocol analyzer. And it's, the lowest level thing you can do with a packet versus just looking at the ones and zeros. Don't you think?
Yeah, exactly right. This is where it all starts. Right? We talked about in the intro slide how we capture ones and zeros, and this is the first, what I would consider to be the first conversion of taking those ones and zeros and making them something that is human readable, right? And that's exactly what we've done. What's in black, like we point out in the bullet, really does come from the packet itself. It's just formatted into, rather than ones and zeros, into the ASCII that represents the bytes, so that we can see them, a little more clearly. But still, it might not make a lot of sense to people. 0x0800. What does that mean? Well, that's why in The gold, we actually do an interpretation of that for you. So we'll tell you what that means, right, from that field. So even here, tremendous amount of details, tremendous amount of work that goes in to decode. And one other thing I think to keep in mind with decodes is, every different type of packet, different types of protocols, et cetera, it gets decoded differently. So that's one of the values of the product. We're able to do that deep decode of each of the individual types of protocols that are available on the network.
The packet header, right, Jay?
That's absolutely right, Chris. And that's always the first thing that I'm looking at, especially if we look at wireless. There's a lot of information in the wireless packet headers. Happens to be a wired packet, but always the first place that I look in that packet.
And in that packet header, what's going to be common to all the packets is, of course, a packet number. Now, this is something that is added to the packet in all of these fields. So we add a packet number, we add the flag, we add the status, we add the packet length, and of course we add the timestamp.
Yeah, Chris, several things on timestamps, really, but starting there and working backwards. Yeah, that flow visualizer to me is, once you get used to using OmniPeak, it's a very powerful view because it's very easy to see where the delays are. Right here, you're looking through a flow, and right at the very top, you see, whether it was, we waited 1.92 seconds, right, for a response to come back from the server. You already know there's problems, right? And then look, the very next line below that, over all the way at the right, there's an expert event, busy network or server. So it's finding those errors for you, on the basis of those delays. But even more basically on timestamps, timestamps are an area where I've actually answered a lot of questions over the years. Right, questions come up a lot about timestamps, and mainly about the accuracy of timestamps. And you were just talking about that, the granularity that's there. But I think the most important point that I always make in the answers to people is, you are right. It matters tremendously where you capture it, but more to the point, it's truly a relative measure, and you even highlighted the relative column right in that screenshot on the right. I mean on the left, and that's absolutely what's important, right? You're never going to know the exact time of a packet, but what is the exact time? Exactly when it came through this switch or router, or when it left the client, or it's going to change a little bit, right? Maybe by only nanoseconds, it's going to change a little bit, but the relative part never lies, right? So when you're trying to make a comparison between packets, as long as you've captured at the same point, that relative measure is absolutely an accurate measure, right? It's an accurate measure of the difference between the two packets. And to me, that's always the best way to think about timestamps and the best way to use timestamps.
So that's really interesting, Jay. And I think that the most important point there is how important timestamps are, but not just the importance of the timestamp, the different ways in which people use the timestamps. Not only does the product use timestamps in different ways, but people do. You're a big fan of the relative timestamp. I'm a big fan of the delta timestamp. I like the delta time between each packet, which is just another way of looking at relative time. But in delta time, the application has done the work for me. So I'm just lazy. So I like that I can just see, from the amount of time between each packet. So I immediately see, for example, the outliers, these guys here, 2.6, 3.4, 3.3, that's going to stick out to me maybe a little bit more than if I'm looking at an absolute time or a relative time.
I think you're right, Chris. I think the difference is maybe what we're pointing out, and haven't said it directly yet, but maybe we'll say it directly now. Maybe the way you use the timestamp depends on the view that you're in, right? Like, for me, delta time is very useful when I'm looking at a particular flow, because then I'm really comparing the packets in one specific flow, and then the delta time, is already done all that work for me, right? That's why there's the flexibility in the product, right? Depending on what you're trying to do, there's different ways to look at that data, and they're all valid and all important.
So here we are at really what I think is the heart of our theme today about packets not lying, and that's the checksums. And the reason is, in a protocol analyzer, or I should say really in the protocols, there is a lot of work being done at each layer to verify that that layer has not changed since the last hop. So, what the analyzer does is display the header checksum, as you can see here. And if that checksum has changed, it's going to point that out. And so I've got an example here where on the left, we've got a packet with some header checksums. We got the IP header checksum. We've got the TCP checksum. And then what I've done is something fun in OmniPeak, where I was able to save this packet and then make changes to it, read it back in, and over to the right, we see what happens to the checksums, or at least the analysis of them when I made those changes. So first of all,
what did you change from left to right?
Yeah, so over here on the left, we'll start with the IP layer. I've changed the differentiated services where it was 0, and we changed that to FF. And by making that change, and very rarely are you going to have the differentiated services of FF. So you might notice that already. But in this case, I'm making it very obvious what got changed. And in doing so, OmniPeak has identified that that checksum is invalid. So the original checksum is still there. So I didn't change that. And now OmniPeak is saying, hey, the checksum that's there and what it calculated as a checksum are different. And really this new checksum is 5EC3. So right there, this is a packet that you're going to throw out. So, it depends on what you're trying to troubleshoot. But no matter what you're trying to troubleshoot, even if it's a performance problem, latency jitter, and you see that your checksums are invalid, whoa, full stop, we've got a different problem. And this happens. So certainly in the case, now it may have gone from a performance issue to a security issue. Maybe you got a man in the middle, who knows? But I think this is a pretty good example of how the checksums, or the values can change, and checksums can be recalculated at all layers. That's why I did it for TCP as well, where we started with a destination port of 54518, and I went in and I changed that to, a fictitious number, 65535. And well, what do you know? The checksum was recalculated, and OmniPeak identified it as this checksum as invalid, and is saying what the original checksum, what the new checksum would be. So pretty important feature of a protocol analyzer, pretty important feature of protocols. So that's why, not only does IP and TCP have checksums, but there are many different protocols that have checksums as well. And usually it's just a hash. I think most of the TCP, the checksum hash algorithms are the same. There may be a few variations, but pretty standard. Now, I wanted to point out, just as a small tangent, how I did that in OmniPeak, because it also goes at the heart of packets don't lie. And packets don't lie unless, because what I like to say is packets don't lie, people lie. So what I did is I used a feature in OmniPeak. What I did is use a feature in OmniPeak to save a packet or a whole packet file or a selection of packets as a text file. So you see, we were looking at the packets before in OmniPeak. I was then able to go save the packets and then save them as raw packet data, star.txt. And then if you open that file up in Notepad, this is what you're going to see. Raw packet data looks very similar to the hex view and the ASCII view. And then I went in with Notepad and I changed those values from the original to FF, to a bunch of FFs. And then I saved that. And then I was able to reread it back into OmniPeak. So OmniPeak can read that TXT file and then display it, as if it were a PKT file. So, unique feature. Most people aren't going to know about that. Probably not a whole lot of use cases, but if you need to do that, I've been doing it for a long time, and it does come in handy. So another really useful mechanism in really protocols, in this case TCP, is the concept of sequence numbers and acknowledgements. Now, with TCP, it's guaranteed delivery. So, for every packet, there's a sequence number that goes with the packet. And then for that packet, there will be an acknowledgement coming back. And this can be used as another way to validate the integrity of your packets. But in this case, it's more about the order of the packets and whether the packets actually made it or not. But there is something to be said about the theme being packets don't lie if you follow the sequence and acknowledgement numbers.
Yeah, I think that makes sense, Chris. And like you say, this things like this help us as we started, developing here, right? And we're going to start transitioning from packets to flows. Some of this kind of information is very useful within OmniPeak, within the protocol analyzer, to be able to start to build flows from packets to know how to go do that.
So up to this point, we've been talking about packet decodes and all the individual fields of the packets and how those can be used to validate the integrity of a packet. But that extends to the higher level analysis as well, where we're building the packets into flows, into calls, we're generating events. But even at those high levels, it's all still coming from the packet with the ability to, at any point in time, drill back down to the packets. And I know Jay and I both really love the ability to adjust those events. Really a lot of the higher level analysis in OmniPeak in our LiveWire products can be adjusted, but the events in particular, being that there's around 200 of them or so, they can be turned on and off. You can change the severity. You can enable or disable them, because you may decide one's maybe too noisy or ones that we had off by default you want on. In fact, the checksum expert event, turns out that's off by default because it can be a little noisy, but you might want to turn that on in a forensic search, maybe not in real time, but in a forensic search. And so, depending on your use case, you can configure the experts to how you want them. But the important point here is that, no matter how they're configured at any point in time, you can always drill back down to the truth, to the individual packets. And with that, I wanted to leave this last slide about packet payloads to Jay, because it really does show the flow from the high level analysis to the payloads.
Yeah, thanks, Chris. I mean, to me, this is a great example in many ways where it summarizes a lot of what we just talked about. It introduces one last part of the packet we haven't talked about yet, packet payloads, and at the same time ties into the expert stuff that Chris was just talking about. So just to give you the background on this actually was from a real customer. It was an application that was used, to drive a phone tree set of commands for like a tech support group. And the customer was complaining about really, really slow response times, to the point where it was very difficult for the people on the phone because the next question or answer wasn't coming up fast enough, and they would have to kind of dance while they were waiting for the next answer. So, of course, we used OmniPeak and packet analysis to go and help them solve this problem. So, of course, for every packet has a payload. And nowadays you're going to find maybe more packets are encrypted, but in cases like this, If it's an internal application, maybe it's not encrypted, right? Because it's all inside behind your own firewall. Or if it's your own application, you also probably have the keys to decrypt things. So you can pretty much in these kind of cases still always get to the payload. And what I love about this example is it's a fairly simple workflow to show you how you can go from an expert event, again, something that Omnipeak analyzes, in this case, a SQL Server client error, which you see in the top graphic there highlighted in that brownish color, right? A quick click in the application of that expert event then highlights the packet in the flow where that expert event happened, which is in the next graphic down, also in that same light brown color. You see packet 13274. You see as you go across all the way on the right, you see the expert event column, and the columns aren't labeled, but it's the expert event column, and it says SQL Server client error. So we found our exact packet. And then by just, again, pivoting one more time and doing a select related packet by expert event, or by just going and looking, double clicking into that particular packet, we could see, again, in the decodes, in some of the views we showed earlier, you can see the payload of the packet as well. And in this case, you see in that payload, it said your server command was deadlocked with another process and has been chosen as the deadlock victim. Rerun your command. So what this clearly shows, and again, this was all based on packets, right? All on those original ones and zeros. Again, none of this lies, right? This is actual data, and the data was verified through checksums and all of that, right? Came out of the payload, and it basically tells the network engineer that this issue is obviously not a network problem. It is an application problem. They're having a database problem where they're trying to two different processes are trying to change some record in the database at the same time. One of them's deadlocked and one of them lost. And that's this particular flow that we're looking at. So it's a great way to summarize everything we've talked about, bringing it up to a higher level, way past ones and zeros, way past individual packets to start with, building it up to a flow, analyzing that flow, finding an error, coming back down to the packet to then show exactly from the packet, what the error message is, and really kind of verifying for all of us that the packets really don't lie. They tell you exactly what is going on the network.
So yeah, thanks for that great example, Jay. And with that, we're going to wrap it up. I hope this has been useful to everybody. Packets don't lie. There's lots of analysis that we can do with packets, but they're really all based on packets. So thank you very much, everybody. And with that, we're going to give it back to you, Stacy.
Thanks, Jay and Chris. So we did have a couple questions that came through from the audience today. I want to make sure we address those. The first one was, what if I come across a packet that Omnipeak doesn't decode?
I'll take that question. I've been writing decoders for many years, and what's great. One of the great things about Omnipeak and Livewire is you can too. Not that you want to, but it is possible. The decoders are in text form, shipped with the product, and we do have customers who implement their own develop their own applications, have their own protocols. So you could go in there, change our decoders, and add your own. Having said that, you don't need to do that for any standard protocol or application. You just let us know, and we're committed to providing decoders for all known applications and protocols. So just let us know. Now, one thing to add to that is there's decoders, and then there's the ability to identify particular applications on maybe non-standard ports. And for that, you don't actually have to use a decoder. There is a built-in feature to add custom ports.
Great, that's awesome. Thank you, Chris. Another question that we had was, how do I see packet payloads when my network traffic is encrypted?
And that's a much tougher question because it's encrypted. So you're not going to be able to see the decode of the encrypted part other than, a line of text saying, oh, this many bytes long. But the point that I'd make there is, unless you're doing some kind of, specific, maybe application troubleshooting or, security investigation. Everything you need to troubleshoot the network is in the the network layers. Ethernet, IP, TCP, and most of the analysis that OmniPeak does is on those layers. So, I think most protocol analysts would agree that you can still troubleshoot your network without having to decrypt the payloads. But if you do need to decrypt the payloads, we have that feature, and you just got to have the right packets and have your your passphrases or shared keys or those kinds of things. So it can be done post capture if necessary.
Cool. All right. Another one that came in, it looks like more of like a clarifying question. So this person was asking, it's not clear how it can be identified if the issue is on the network or in the application. So how does this work, or how does this help?
Right. So this is truth really at a different level, versus is the packet lying or not, is this could get back to, people lie, because somebody might say, well, it's the application. Not that they're lying, but they might think, well, it's not the application, it's the network, or vice versa. There's always this finger pointing, and OmniPeak is great for being able to verify very quickly whether the slowness of the network is the network, the latency is the network of the application. We have a feature in Compass called two-way latency that will show you the network latency and the application latency overlaid in the same graph. And, there it is in front of your eyes. So if you haven't tried that out, load your trace file into Compass, change from utilization to two-way latency. And we call it the money shot because, right there, you're pretty much done. If you have application latency, then, well, you can use other parts of OmniPeak, other features to get more information to give to the application guys. But in most cases, actually, I guess in most cases, it will be the application, because in my own experience, the network latency is usually sub-second, and that's a great way to take a look at that. And we've done a video on it. We have a write-up on our website about that. It's called the Network Health Assessment, and there's a video that goes along with it. So check out our website in the blog section.
Fantastic. Well, thank you, Jay and Chris. So for all of you out there today, how can we help you out? So we're hoping that today you've gained some additional insights into how LiveAction solutions can work to enable network teams to address some of those key challenges around that granular part of your network. In order to get some additional insight, you can take a better picture of how LiveAction can help deliver these successful network operations by reviewing today's webinar or sharing it with a colleague. Or you can also explore the LiveAction channel on Bright Talk to view any of our past webinars for some additional insight. Today was the third episode of our Journey of a Packet, so there are some previously recorded webinars available for you to review if you haven't been able to see those yet. You may also decide that you'd like to have a more personalized one-on-one live NX or LiveWire demo session for you and your team, so we're happy to get that scheduled for you. Or you might want to download a free trial to test out in your own network. All of these resources can be found in the attachments tab of this webinar, as well as some additional resources. So with that, I'd like to thank you all for attending today's webinar and remind you that we do have part 3 of our Detecting Advanced Threats webinar series. This one's going to be titled Incident Response and Triage, and that's going to be held next Wednesday, March 30th. So you want to make sure to pre-register for that so you don't miss out. If you're not part of the SecOps team or you're just interested, you might even pass this along to a colleague on the SecOps team of your company. Thank you again, everyone. We're looking forward to seeing you at the next session and hope you all have a great rest of your day.